So a vector in Rn with length 1 is called a unit vector. If x is a non-zero vector, then we can define a unit vector in the direction of x. So that vector is given by this expression here, u. So this is the scalar multiple of vector x by 1 over the magnitude of x, or the length of x. Okay, so remember here we are performing scalar multiplication. This is a scalar, this is a vector. And with the notion of dot product, we can define the notion of parallelism. Two vectors, x and y, are parallel if x is a scalar multiple of y for some c, or if y is a scalar multiple of x for some scalar. So here, if the scalar c is positive, then the vectors x and y are in the same direction. Otherwise, they are in the opposite direction. So with the notion of a length, we can define the distance between two vectors, x and y, and that is obtained by taking the square root of the inner product, or the square root of the dot product of x minus y with itself. Okay, so it's the length of the vector difference x minus y. That is the distance between x and y. So to illustrate these definitions, consider in R4 the vector x as shown. So the distance formula implies that, or rather, the definition of the length implies that x has length equal to square root of 21. Okay, this is the square root of the dot product of x with itself. 0 times 0 plus -2 times -2 plus 1 times 1 plus 4 times 4. In R2, consider vector y as shown. Its length is equal to 1. So this is an example of a unit vector in R2. In R4, we can compute the distance between vectors x and y as shown. So by definition, we just take the square root of the dot product of x and y, or rather, the square root of the dot product of x minus y with itself. So take the x minus y, the vector x minus y, that is given by this vector here. And then you take the dot product of this vector with itself. Then you take the square root. That's what happened here. So some remarks about the length. So note that if c is a scalar and x is an arbitrary vector, then the length of the scalar multiple of x by c is equal to the product of the length of x and the absolute value of c. Okay, so remember that the length is always a non-negative number. So if c is, for instance, negative, then you have to take the absolute value. We also have the inequality of Cauchy-Schwarz. So this says that if x and y are vectors in Rn, then the absolute value of the dot product of x and y will not exceed the product of the lengths of x and y. Okay, so remember x dot y is a scalar. Okay, this and this are scalars. So the quantities involved here are all scalars. So in the left-hand side, we are talking about the absolute value, the usual absolute value of a real number. And an important consequence of Cauchy-Schwarz inequality is the triangle inequality, which we are all familiar with. So this inequality says that for any vectors x and y, the length of the sum, the length of the vector sum, will not exceed the sum of the lengths of x and y. Okay. So we can easily imagine this by the parallelogram law in adding vectors. And also, we know from elementary calculus that in R3, the dot product allows us to define the angle between two non-zero vectors, and that notion can extend or extends immediately in the case of Rn with the dot product. So the angle between non-zero vectors x and y is given by this expression. So you take the dot product of x and y, this is a scalar, then you take the magnitudes or the lengths of x and y, take the product. So this is also a scalar, then you take the quotient, then you take the arc cosine of that quantity. So to give you an illustration for the notion of the angle, so consider x and y in R3. Okay, so this is vector y 0, 1, 2. This is vector 1, 2, negative 3. So the angle theta is this angle that we drew between the two vectors. And the formula indicated earlier indicates that the angle between them is equal to or approximately 61.439 degrees. So we've defined earlier the notion of parallel vectors. We can also define the notion of orthogonal vectors or perpendicular vectors. So two vectors are orthogonal or perpendicular if and only if the dot product of x and y is 0, the 0 scalar. And if this is the case, we will write this x perp y, x perpendicular to y. For instance, in R4, these two vectors are perpendicular because their dot product is 0. So you can check. Note that when we try to solve a linear equation of this form in n variables, then we are actually finding all vectors x1, x2 up to xn that are orthogonal to the vector whose components are the coefficients in the left-hand side of this equation. So given a set S of vectors from Rn, we will say that vector x is orthogonal or perpendicular to S if and only if x is perpendicular to y, or x is orthogonal to y for every vector y in S. Okay, so in this case, we write this notation x perp S. So in the last slide, we defined orthogonality between two vectors. So here we are defining orthogonality of a vector with a set of vectors. Okay, so this this race is crucial in this definition. So we define the orthogonal complement of S to be the collection of all vectors x that is perpendicular to every vector in S. Okay. So S perp is our notation for the orthogonal complement. So it's the set of all vectors that are perpendicular to each vector in S. So note that if S is a set of vectors in Rn, a vector that is orthogonal to S is also orthogonal to the span of S. In other words, the orthogonal complement of S is the same as the orthogonal complement of the span of the set. So to illustrate the definition, consider R3 with the dot product. Consider the vectors x, y, and z as shown. So by definition, the orthogonal complement of the set containing x, y, and z is the set of all three vectors, okay, that are orthogonal to x, to y, and to z. Okay, so it's the set of all vectors satisfying these simultaneous equalities. Okay, so this is S-perp, or the orthogonal complement of S. In other words, the orthogonal complement is the collection of all vectors x, y, z satisfying this system of equations. X plus y plus 2z equals 0 is obtained from this first equation by performing the dot product operation. And similarly, the second is obtained from this equality. The third equation in this system is given by this equality. Okay. So the orthogonal complement is the collection of all vectors satisfying this system, this homogeneous system of linear equations. The constant of vectors is the zero vector. So S-perp is nothing but the null space of the matrix A, which is the matrix of coefficients in this homogeneous linear system. Okay. So observe that the columns, rather the rows of this matrix A are the given vectors x, y, z. Okay, x is the first row, y is the second row, and z is the third row. If you take the transposes of these three given vectors. The dot product also allows us to define the notion of projection, of a projection. So for any given vectors, x and y in Rn, such that y is non-zero, the projection of x on the vector y is given by this expression. So this is a scalar multiple of vector y. So recall from Math 22 that in R3, the projection of x on a vector y is the vector along the line defined by vector y that is closest to vector x. Okay, so we can see from this illustration the projection and we can verify easily that this scalar here is the proper or the correct scalar for the definition of the projection, because if C is a scalar such that vector x minus cy is orthogonal to y, in other words, x minus cy dot y is 0, then solving this equation will give us C equal to x dot y over y dot y. Okay, so this vector here, if this is vector y, this vector here is given by this yellow vector. So this is the orthogonal projection of x on y. So you can think of the vector projection or the projection of x on y as the shadow, no, of vector x on the line containing vector y. If there is a light, say there's a light lying above vector x.